Okay, so the next slide here again refers to what is the meaning of the term Miller indices of Miller indices of family of planes. We saw in my last example that it was with reference to a cubic system. Here it is not with reference to a cubic system. This happens to be a tetragonal system, which we are trying to show it here. The tetragonal system where you have the A, the B, the C is here. So A is equal to B, not equal to C is what I observe here. And if you want to understand that what can be the family of planes for 100 type of planes, so I need to understand that where is the 100 plane. If you recall, the 100 plane in this particular case will be, it will have one intercept on the x-axis parallel to the y and the z-axis. So the front face of this cube, this plane will be represented by an index of 100. This will be represented by 100. Similarly, now we have the, so this is representing 100, and the rear face of this cuboid here, this particular plane, will be then represented by index which is 1 bar 00. 1 bar 00. So I have two planes, the 100 plane, and which is shown here, and this particular face happens to be represented by your 1 bar 00 plane. So these are the two planes which we are trying to show here. Similarly, I have the 010 plane. If anyone can tell me where will be the 010 plane? This plane will have an intercept of 1 on the y-axis. So the 010 yeah, 010 plane will be this particular plane. I can say this will be indexed at 010 plane, and then I have the 0 bar 10 plane, which will be the left hand face. So this face will be then referred to as 0 bar 1 and 0 plane. We are trying to say here that they all belong to a family of planes of the type 100. What is the difference here from the cubic unit cell? We have excluded the other. There are two more faces which I have excluded here. The ones which we have excluded are the top and the bottom face of the cube. This one has been removed. This has been excluded. I'm not saying that it is a part of the family of 100 plane. This will be initially, what will be the index of this? It will be indexed as 0, 0, 1. And the bottom face will be indexed as 0, 0 bar 1. So the family of planes which belong to 100 in this particular tetragonal system, they are actually 100. This is 1, then 1 bar 00, then we have 010 and 01 bar 0. Why 001 and 00 bar 1 are not included here? Why they are not in the family? Because
sir, A is equals to B, not equal to C.
Yes, yeah, because we said earlier, today we'll go give more information about that why they are crystallographically equivalent. Here we see that 001 and 00 bar 1, they are not equivalent to these four planes that you are trying to establish here, because their dimensions of these planes are also different. So they are having B and A as the dimensions here. They have a different area. So I am actually introducing that their area is different from the front and the back face and the right and the left face. Whereas the four planes that I show here, they have the same area. They have the same area. Not only area, we will see later on that they have the same number of atoms as they are contained in this particular plane. So that is another way in which we will see that they are crystallography equivalent. So a family of plane means different for different systems. For a cubic system, there were 6. For a tetragonal system, for 100, there are 4. Okay, let's move forward here. And I have one more problem, which is a simple one. So I already indexed it here. Its intercept on the x is 1 by 2. So it is actually plus 1 by 2. Then its y-intercept is 1. So it has an intercept of 1 on y, half of on x, and then 1 on the z-axis. And this gives me that the intercepts are half, 1 and 1. The reciprocal is 2, 1, 1. And the plane that is shown here right now in this figure is then indexed as 2, 1, 1. So this is how this plane as such will be indexed as. Let's go forward. Similarly, there's another problem. I leave it. Let's come to one more example here. Let me remove this too much. So we have one more observation here, which is very, very important for us. The observation is that it is only valid in the case of cubic systems. It is only valid when you have a cubic system being discussed here. And what we see here is that this observation tells me that this observation tells me that for cubic systems, the Miller indices of a plane, and its normal direction, they are identical in a cubic system. The Miller indices of a plane and a direction which is normal to that plane, they are identical. There is some misprinting here. This shall be read as U, V, and W. So this is what we are trying to understand here. The simple way to understand this concept is I'll just draw a unit cell, and then we will be able to appreciate that what is written here. If I draw this unit cell, and then try to create one of the planes on it, and if I say I want to index here the 100 plane, that where shall be the 100 plane? It shall have an intercept of 1 on the x-axis parallel to the y and z. So you have your x, y, and z being shown here as positive, and positive. So going by this notation, the front face of this cube will be then represented as the 100 plane. Is it okay? Is it okay?
Yes, sir.
Yes, sir.
So now
Yes,
this observation tells me, or this assertion tells me, that Miller indices of a plane, right now let us say this is the plane. So I have 100 Miller indices of the plane 100, which is h, k, and l here, and its normal direction, and a direction which is normal to the plane, to this particular plane, they are identical for a cubic system. Only for a cubic system they are identical. So if I look at that, where is the direction, where is the normal direction? Now you can try to see that if I mark a direction which is normal to this plane, which is indexed here as 100, let us say I say this is the direction. So this is the direction which I am trying to say is the normal direction, a direction which is normal to a plane indexed as 100. And incidentally, I can now have the information about the index of this direction also. So if you remember, the directions are indexed by creating the origin on the index. So I take this as the origin, then the coordinates of the other point are red, and the coordinates of the other point are 1 in x, 0 in y, and 0 in z. So the direction, the normal direction here is then indexed as 1, 0, 0. And this is precisely what we are trying to say, that whenever I refer to a cubic system here, the direction which is normal to the 1, 0, 0 plane will have, this is the HKL index of the plane, the normal direction to this plane will have the identical Miller indices 1, 0, 0. So the U, V, W will be equal here. Similar is true that if I am talking about the 1, 1, 1 plane, so a direction normal to the 1, 1 plane, so this is the HKL value, and a normal direction, a direction which is normal to this 1, 1, 1 plane will be then indexed as the 1, 1, 1 direction. So this is an observation which is valid, and we say it is valid in the case of cubic systems only. Again repeating, for a plane having indices HKL, the direction of the normal to the plane is also indexed as UVW equal to HKL. So this is what is the observation for a what we call as a cubic system that you are referring to right now. Okay, I hope it is clear. So let's move forward. So we now introduce two more concepts today, although the assignments regarding this are already with you. But I introduce the concept of linear and planar densities today in this class. It's an easy thing to understand and won't take much of your time here. So linear density is applicable in the case of directions. So when I talk about crystallographic directions, just like the one which is shown here as 110, so for the case of direction, the term linear density will be used. And what is the definition of this? The linear density here we are trying to show. We have shown here the linear density for we have shown a linear density for a direction which is referred to here as 110. So this red arrow here is showing you the 110 direction. I hope you can understand that why it is 110. So the origin is here. So you have one intercept on x, one on y, and 0 on z. That is why this direction is referred to as the 110 direction. If you want to calculate the linear density on any direction, be it this or any other, the formula is simple: number of atoms centered on the direction vector that you are trying to index divided by the length of the direction vector. Number of atoms centered on the direction vector divided by the length of the direction vector. Here, something which we need to add on is that we will count only the atoms. If there are half of them, we'll count them as half. If full of it is contained on the direction vector, we will count it as one complete atom here. Going by this observation, or going by this formulation, and what I observe here in this CCP unit cell. So I have a CCP or a FCC unit cell in which the 110 direction has been indexed. So we find here that I have one complete atom located here at the center, and half of it is here and half of it is here. The same thing is shown here now in 2 dimensions. So if I look at it from the top view, this is what is observed here, that you have the corner atoms here, and there is a one y which is referred here as y here at the center. So this is y, this is x, and this is z. If I look at it from the top, this is how it looks like. And going by this, I find that the total number of atoms are 2. One is here, the y1 is totally complete, and then there is half of x and half of z atom which is available. So this gives me a total of 2 atoms. And what is the length of this direction vector? The length of the direction vector 110 happens to be 4 times r. 4 times r means it is 2r plus 1r plus 1r, so it is 4 times r. So LD, linear density with a subscript 110, it is how it is written here. It is now found as 1 upon 2r. And there is one more statement which we make here, that crystallographically equivalent directions shall have the same linear density. We already defined crystallographically equal directions earlier, where we find that we find adjacent, we find similar neighboring nearest neighbors there, but we add it with the help of this linear density concept, and we say here that the directions which are crystallographically equivalent They shall have. They shall have. Shall means essentially they shall have same linear density. So this is what we observe here, and this is what we see that what is the meaning of the term linear density as far as any so linear density is concerned with the directions here, crystallographic directions in this particular example here. Okay. The next thing that we now talk about is planar density. So this one is now planar density. Very clear that planar density will be applicable to planes, which may be indexed as 110 or something like others. So if I talk about 110 plane, so I am talking about then the PD value, the planar density for 110 plane or 111 plane. Let us see how we find out that. So the formulation is simple. The number of atoms centered on the plane divided by the area of the plane. So this is the planar density concept that we observe here is applicable for any system, whether it is cubic or non-cubic. The definition of planar density, linear density remains the same. So number of atoms centered on the plane, again complete ones will be counted and divided by the area of the planes which is available to us. So if I look at this figure here, this one, and I can see a plane which is indexed here, let us say this one. So can someone tell me what is the Miller indices of this particular plane, which is we have shown here as with a sectioned view? The Miller indices of this plane are, which is
1, 2.
It is this one.
1, 1, 1.
Yeah.
Sir, 110.
1, 0.
Yeah, it is 110. Commas are omitted. So we have this plane which I'm trying to show to you, and we are trying to see that what is the Miller indices of this particular plane. So for that purpose, the intercept has to be there. I'll choose the origin here, let us say, which is not on the plane. So intercept on x is +1. Intercept on y here is again +1, and it is parallel to the z-axis. So the intercepts are 110, and if I take the reciprocals again, there are 110, and that is why the plane is indexed as the 110 plane. It is indexed here as the 110 plane. Okay, is that right? And if I am looking at this crystal structure, which type of it is? Is it face centered or body centered?
Face centered.
Sir, face centered.
This happens to be FCC or CCP if it is a cubical system, cubical closed pack or FCC. So we see here that I have indexed here plane 110 on FCC in a FCC crystal structure, and if I look at it in 2 dimensions, it is how it looks like. So the planes A, B, C, D, E, F, they are just shown here. Here, this is what you observe. So you have the planes A, B, C, D, E, F. The B and the E planes, they are at the center of the face, and A, D, E, F, they are at the corner. So the total atoms that are available to us are, the total atoms available are half of this, 1/4 of this, 1/4 of this. So you have the number of total atoms still remains 2. That is, this is 1, and 1/4 into 4 is again 1. So the number of atoms is 2, which are centered on the plane, and then the area of the plane. The area of the plane can be calculated here as, if A happens to be the, if it is a cubic system, I can say A, this is A and A. If A happens to be the lattice parameter, I can calculate the area of the plane ACDF. ACDF. Can we do that? It
Yes,
will be
sir.
A multiplied by the diagonal, the face diagonal, which is nothing but
A root 2.
A root 2. So we have ACDF area given as A into A root 2. And I already know, here I find it is in terms of R, that is atomic radius. And we already know that for a FCC system, we already know the relationship between A and R. For a FCC system, A is written as 2R into root 2. So this formulation is already available with us. So A is written as 2R root 2 for a FCC system. And going by that, I can convert this, I can just put in this value and I get that this 1 upon 4 R square root 2 happens to be the planar density of this particular plane indexed there as 1, 1, 0. Same concept applies here, that crystallographically equivalent planes will have the same planar density. Crystallographically equivalent planes will have the same planar density. So this is what we already know in the case of crystallographic directions also. If they were told to be crystallographically equivalent, they had the same linear density concept there. Is it clear? Okay.
Yes, sir.
Let's move forward. These are two examples where you just want to just reinforce what we are learning here. So if this is a sketch in your figure here, which is on the left hand side, I say it's figure number 1, this is figure number 2, which you observe here. So in this figure number 1, if I ask you to sketch the atomic packing of the 100 plane for a, let us say it is a BCC crystal system, which is shown here. So the atomic packing of a 100 plane. Can we do that? The 100 plane is very simple to locate. Front face, this one. So this happens to be your 100 plane. And if I look at the 100 plane and draw it in the form of reduced atom model, this is what we observe here. That you have atoms which are at the corners here. Is it right? This is how the 100 plane is shown there. And its planar density is also, you can calculate the planar density if I know that where are the atoms located here. Similarly, I have a FCC system shown here, and if I want to index a 201 plane. So for a 201 plane, if I say the intercepts will be now, on the x-axis it will have an intercept of half. On the y-axis it will have an intercept of infinity. And on the z-axis, it will have an intercept of 1. These are the intercepts which I can foresee from the given Miller indices, which are already known to us. So you have the Miller indices given to us. So we are going backwards, calculating the intercepts here as half, infinity, and 1. So the plane that you are going to get here is the one which is parallel to the y-axis. The plane that you get here is parallel to the y-axis. It has a half intercept upon the x-axis and 1 on the z-axis. So this was your 100 plane that you observe, and this happens to be your 201 plane. This happens to be your 201 plane. If I look at this 201 plane, this is how it is. It will look like, and this is an FCC system. So in an FCC system, we observe that if I draw this plane in 2 dimensions, so where are the atoms located? Where are the atoms located for this 201 plane? The atoms are again at the
Corners.
not at the corner. Sorry, just a minute. It's a bit wrong here. It is at the corners, the top 2 corners. That's right.
2 corners and
Yeah, they are at the corners. So this one and this one, they are shown here, and there is one at this face centered, which is available to us here. So this is how we can see that this is how atoms are located on a 201 plane in a FCC crystal structure. This concept will help us in solving the problems which we look at it in our next slides today, which take forward the concept of crystallographically equivalent planes. I hope it is clear to us by now what is being discussed. If there are any queries, you can ask. I'm recording today's class and put a video on this because The previous recordings are not that good. So I'll delete that and put this one. Okay. Let's move forward and go to one more exercise and an interesting one. So the problem states that you want to find crystallographically equivalent planes for this particular unit cell. So the unit cell is already given to you. And if I look at this unit cell, I can simply see that here, if this is A, this is B, and this is C, obviously this is not a cubical unit cell. This happens to be a tetragonal P type of unit cell. Primitive because the atoms are only at the corners here. The angles are already written as 90 degrees, so this happens to be a tetragonal P unit cell. The question is that there are three parts of this question, and we'll do it in separate slides. So the first one is regarding part A, which says that out of these three planes, 0, 0, 1 bar, 0, 1, 0, and 1 bar 0, 0, which are crystallographically equivalent. So the first step is to draw these planes, and then we will understand that whether they are equivalent or not, then we'll apply some logic and the definition of crystallographically equivalent planes. So the first step is to draw these planes 0, 0, 1 bar. So we start with 0, 0, 1 bar plane here, which we will try to draw in this first unit cell that is shown here. So without going into further any because it's very simple to draw. It has infinity intercept on x, infinity on y, and -1 on the z axis. So it's parallel to x and y, but it has an intercept of -1 on the z axis. So if I choose my origin here, we have this as x, sorry, this is y, this is x, and this is plus z, plus z. So this is minus z. So the plane here happens to be 0, 0, 1 bar. This is the bottom face. So this happens to be your 0, 0, 1 bar plane. Is it right? Is it okay?
Yes, sir. Yes, sir.
Okay. Then I go to 0, 1, 0. So let's draw 0, 1, 0 here. 0, 1, 0 has an intercept of 1 on the y-axis parallel to the x and y, x and z, sorry. So it has an intercept of 1 here, which means the plane we are referring to is this one. This is the plane which is referred as 0, 1, 0, and where this was taken as your origin here, and you said that okay, this is the plus x direction. Similarly, this is the plus y direction, and then this is the plus z direction. So this plane is parallel to the x direction, parallel to the z direction, and having an intercept of 1 on the y direction, positive 1. And this is the plane which I locate as 0, 1, 0. 0, 1, 0. Then the third plane is 1 bar 0, 0. 1 bar 0, 0. And if you recall what we were doing in our previous slides, it is very easy to go there, that it is having an intercept of -1 on the x, parallel to the y and the z axis. So I locate my origin here, where it is x here, this is y here, and this is z here. So this is positive x. Going by this, this happens to be minus x. So it has an intercept of -1. So it is for 1 bar 0, 0, -1 intercept on the x-axis, which is here, parallel to the y and parallel to the z, which means I am referring to this particular plane. So this is the plane which we have indexed there as 1 bar 0, 0. So I have indexed these planes, the three ones which are shown here, 0, 0, 1 bar, 0, 1, 0, and 1 bar 0, 0. The question is which of them are crystallographically equivalent. So now let's go back to what was the definition of crystallographically equivalent planes. We said they shall have the same area, they shall have the same planar density. And obviously, if you go back to without the concepts of planar density and the area, we already know that they shall have the same location, they have the same lattice parameter, they shall have the same location of the atoms as such. So going by this logic here and the definition of crystallographically equivalency, can you now see which of these three planes are equivalent to each other, or all of them are same, equivalent, or there is a difference here?
2 or 3 are
Z1 is
equivalent.
not equivalent.
We observe here that the plane here, which is shown as 001 bar, it has the dimensions 0.3 into 0.3. So the area will be 0.3 into 0.3 nanometers. The plane described here as 010 has dimensions of 0.3 into, this one is 0.4 nanometers. So 0.3 into 0.4. And incidentally, the 1 bar 00 plane also has the dimensions 0.3 here and 0.4 nanometer here. So this tells me that the planes which are here written as 010 and 1 bar 00, these two planes happen to be crystallographically equivalent. Is that right?
Yes.
If this
Yes,
would
sir.
have been a cubic system, then what would have been the answer?
All.
Three
Then
will be
if this would have been a cubic system, all the three ones that you see here, all of them would have been declared as crystallographically equivalent planes. So this is how we decide that whether they are equivalent or whether they are not equivalent. So the first problem is solved. Let us go to the second problem. So now I am looking at the second problem here, which is B. There are four planes which are given here. The step will be again to index them first. So the first one which we say is 1 bar 0. 1 bar 0. So it has an intercept of 1 on the x, minus 1 on the y, and it is having an intercept of infinity on the z. Means it is parallel to the z axis. So if I want to locate 1 bar 0 1 bar 0 plane, I will say that, let us say, this is the origin now. So the choice of origin is important here. So we have this y, we have the x direction, the plus x, the plus y, and the plus z direction. So accordingly, this will be minus y, this will be minus z, and this will be minus x. If I want to locate 1 bar 0, means intercept of 1 on x. So on x, it is intercept is 1. So that means the intercept is here. And its intercept on y happens to be minus 1. So it is here. This is minus 1. This is 0. This is minus 1. So I create a plane which is here. So this is the plane which we refer and index as 1 bar 0. This goes well with the logic which I defined in my beginning slide today, where we saw that if one of the HKL index is 0, then it must be a parallelogram. The plane must be a parallelogram through the corners, and it was valid in the previous case also. Just in this case also, where we saw that if the two indices are 0, then they must be the face parallel to the face. So this is what we saw. They are all parallel to the face, or in this case, the faces themselves. Here, there is one of the index is 0. That is why they represent these parallelograms here. So we have the first indexing done, which is indexed here as 1 bar 0. Let's come to the next one, 1 0 1 bar. So I have the next one written here as 1 0 1 bar. So the intercepts on the x, y, and z direction are x is 1, y intercept is infinity, and the z intercept happens to be minus 1. So it is intercepting z at minus 1, parallel to the y, and having an intercept of x as 1. Is that right? Is that right?
Yes.
Yes, sir. Is it understandable? It
Yes,
is
sir.
too much for you. If you are not understanding, you can ask me and I'll repeat the same thing. So I want to index here the plane which is to be written as 1, 0, 1 bar. So if I want to do that, I'll again need to see the origin here. So choosing the origin at this point, I find that the intercept on x happens to be 1 here. The intercept on the y is not there, because if this is the origin, this is your y direction, negative y. This happens to be your plus x, and this happens to be your plus z. Means this is your minus z direction, and this happens to be the starting point or the origin which we are having. So it is now as 1, 0, 1 bar. So index of 1 intercept here, 0 and 1 bar. 1 bar is here. So now the plane is here. So this is the plane which we will index here as your 1, 0, 1 bar plane. 1, 0, 1 bar plane. So this is how this indexing is done, where we index this as 1, 0, 1 bar plane. The next one is now picking up from the same example, 0, 1 bar 1. So next I want to index 0, 1 bar 1, having an infinity intercept on x, minus 1 on y, and plus 1 on the z. Means it is parallel to the x-axis. If it is parallel to the x-axis, let's take the origin here. So I have this x direction, the minus x direction, the plus y direction. Keep it in mind how I am choosing the origin, just because I have to represent them. So it is minus y direction and plus 1 in the case of z. So this is your z direction here. So it is 0, 1 bar 1. It will be parallel to the x-axis, intercept of minus 1 on y. It is intercept of minus 1 on y here, intercept of 1 on z, plus 1 on z, and the plane is this. So this is the plane which we say is represented by your 0, 1 bar and 1. So this plane represents the 0, 1 bar 1 plane here. Is it clear?
Yes.
Yes, sir.
Okay. Then I'm left with one more, which is 1 bar 1 bar 0. 1 bar 1 bar 0. So where is the 1 bar 1 bar 0? It is the easiest one out of them. 1 bar 1 bar 0. Minus 1 on x, minus 1 on minus 1 on x, minus 1 on y, and parallel to the z axis. I'm again speaking slow. Minus 1 on x, minus 1 on y, and infinity on z, means parallel to the z axis. So I have to locate the origin here then, so that I can represent it in a unit cell. That's how the origins are chosen. So this is minus x, this is plus x, this is plus y, this is minus y. Accordingly, this is z plus and minus. If I done this location, now I say minus 1 on x. So minus 1 on x is here, minus 1 on y, minus 1 on y is here. So I have this plane which we draw. This is the plane which we draw here as now our last one, which is written here as 1 bar 0 plane. So we have drawn all the planes here. The next thing is we need to see whether they are equivalent or not. So let us see, we'll use the concept of the area of the planes, the plane density concept again. So when we look at the area concept here, we can very easily see here that the areas can be now found. So I have the first plane, which is given as 1 bar 0. 1 bar 0 plane. So if I look at this dimension of this plane, this happens to be 0.4 nanometer. The face diagonal, which is the bottom, this one here, you can find out its dimension because it is 0.3 into 0.3. So it is 0.3 square into 0.3 square root of this, and this value comes to 0.424. So this value comes to 0.424. The location of the atoms is at the corners only. When I look at the second figure here, we now see that this dimension again happens to be 0.3 only. So it is 0.3 nanometers. But now I have the face diagonal. So the face diagonal, which one is here? This is the face diagonal, which is now constructed by 0.3 and 0.4, and this comes to 0.5 nanometers. So the dimension is given 0.5 nanometers. Similarly, when I look at the next one, 0, 1 bar 1, so the dimension here of this edge happens to be again 0.3, 0.4, the hypotenuse would be 0.5 nanometers, and the edge length, the base happens to be here again 0.3 nanometers. So 0.3, 0.5, 0.3, 0.5 again here. When I look at the last one visible to us here, so the dimensions here are again, this one is 0.4 nanometers, the height of the unit cell, and the top face diagonal again happens to be equal to the bottom face diagonal, which is 0.424. So going by this, I think now it is understandable that which one of these planes are equivalent. So the answer happens to be quite simple now. The planes which are indexed as 1 bar 0, 1 bar 0, and 1 bar 0. So 1 bar 0, which is this plane, and 1 bar 0, which is the last one which I draw here, they are equivalent. Yes, they are equivalent to each other.
Yes, sir.
Yes, sir.
Yes.
If they are equivalent, what about the other two? The other two, they are also equivalent, but they in a different set. So 4 of them are not same, 4 of them are not equivalent, but in this set they are equivalent. That is the 1 bar 0 that we draw here, and the last one, that is 1 bar 0, they are equivalent. The rest two that we see here are 0, 1 bar 1, and the one which we left is 1, 0, 1 bar. So they are equivalent to each other. So they are equivalent to each other. They are also equivalent to each other. And again, what will happen if this would have been a cubic system?
All three will be
All are
equal.
equal.
So this is a tetragonal P system. If this was a cubic P system, then all of them would have been the same. All of them would have been the same. Okay. I hope this makes the things a bit clear now. Let's move forward. I'll finish up this example today. So let's go to our next, the last one, which we say C. So when I look at C, I say there are 4 planes again. Let's go forward and be fast. I want to draw 1 bar, 1 bar, 1 bar. 1 bar, 1 bar, 1 bar. So going by from the first slide, this shall be not parallel to any of the edges, but it shall be passing through the face, the edges. So it shall pass through the edges. So 1 bar, 1 bar, 1. 1 bar, 1 bar, 1 bar. So if I do that exercise here, now it can be located here. This is the origin. So I say this is your x plus, y plus. This is your x plus. So you have -1 in y, -1 in x, located already, -1 in y, and then I have this is the z axis. So this is your minus z. So I have the minus z located here, -1z, and the plane is then located like this. So this is the plane which we have indexed. So this plane represents the 1 bar 1 bar 1 bar plane. So done with 1 bar 1 bar. Let's go to the next one, which we say is to be now indexed. It is 1 bar 1 1 bar. Please look at it carefully without any hurry. The video will be shared. So 1 bar, 1, 1 bar. I told you already that the location of the origin to show these unit cell, these indices, this plane in a unit cell is important. Otherwise, the construction will become difficult. So again, I choose the origin so that I have the intercept of -1 on x, +1 on y, and -1 on z. So the way we select is that we select the origin here now, so that this can be shown in this unit cell. So this is -x, this is +y, and this is -z. Sorry, this is -z. This is -z. Going by this, this is -1 on x. -1 on x will be here. This +1 on y will be here. -1 on z will be here. So the plane is then located here as this plane. So this is the plane that we locate here as the second plane. So we have located the first one and the second one also. Let's go forward and then try to locate the two more ones which are left here. So we go by the next one. It is 1 bar, 1 bar, 1. 1 bar, 1 bar, 1. Locate the origin again in a way so that you can represent in the unit cell -1 on x, -1 on y, they shall be shown. So if I locate the origin here, this is plus x, then obviously if this was the origin, this is the -x direction. So if this is the plus y direction, this is the -y direction. So by this I can locate both -1 on x and -1 on y, and then +1 on the z. So this is your z axis which is shown here. So the indices, the intercepts are -1 on x here, -1 on y here, and +1 here, and this is the plane which is shown here as 1 bar, 1 bar, 1. This is the plane which is shown here as 1 bar, 1 bar, 1. Now, let's go to the last one which was left in this problem. It was here as 1, 1 bar, 1. 1, 1 bar, 1. Intercept is plus x minus y, plus x minus y, and plus z. So I have to locate the origin here so that it can be shown in this unit cell. So we now have the plus x direction, we have the minus x direction, this is the plus y direction, this happens to be the minus y direction, and then obviously this happens to be your plus z direction. Intercepts of +1 on x, so +1 on x is here, -1 on y is here, and +1 on z is here. So the plane happens to be this. This is the plane which we are showing here. So this plane is then the 1 bar 1 plane. Now, are they crystallographically equivalent, or what is your take on this? Anyone can answer if you have understood that? Are these planes having the same area?
Yes, sir.
They have, because all of them pass through. All of them have the same thing going on here. They have the same this face diagonals.
Yes, sir, they are
Top
classically equivalent.
and the bottom face diagonals, they are there. And then we have these face diagonals from the side and the left and the right face and the front and the other face. So all these planes, all of them are equivalent. This exercise helps us not only in understanding crystallographically equivalency, but also is an example to draw the planes, to sketch the planes, that what, and they convey